So what we're going to look at now are exponential growth models and decay models. And what we're going to be doing is working with a particular kind of model to start exponential growth and decay. We'll look at logistic models, and we're going to do a little bit of conversion, rewriting some of these models from one form to another. Now, we looked at models before, like we talked about variation. If there's direct variation, we have this. Inverse variation, we have this. We could have direct variation with powers of x. We could have inverse variation with powers of x. We could have joint variation. And we could have combined variation. Some direct variation and some inverse variation. And these are all ways of modeling some kind of relationship, some kind of phenomena in the natural world. And then at the beginning of this lecture, I'd mentioned some other types of models, say cyclical models using a sine function, and exponential models, y equals b to the x. So we're going to take a look at some exponential models. So the first one we're going to look at is f of t a0 e to the kt. And we call this exponential growth. For k greater than 0. And we can call this exponential decay for k less than 0. So we're going to take a look at a couple examples with some growth and some decay. All right. So first example, and these are going to function very similarly to what we did with the variation problems. We're going to take our base formula, we're going to find the constants, and then what we're going to do is use that formula to answer a question. So, first example. Let's say in 2000, Israel has a population of 6.04 million. So, and it's projected Israel will have a population of 10 million in 2050. So we want to come up with a formula. If t is years after 2000, find a model for exponential growth. Well, all right. So what we're going to do is try to find a model using the exponential growth model. So what that was again was f of t equals a0 e to the kt. Now we know t is going to be in years. We know e. This is the initial population This is the constant we need to find. Now, with this initial population, we're told that it's 6.04 million. So what's common in this type of problem is we just refer to this as 6.04. And we're going to keep in mind that this is really 604 times a million. So whatever numbers we get as output from our formula, we always have to multiply that output by 1 million, something we're going to want to remember. All right. So this really means million. There's a times 1 million implied here. Well, T is years after the year 2000. So in the year 2000, population is 6.04. And there's times a million, 60, anyway, hopefully you've got it. So it's really 6.04 million. And this is for T equals 0. Because remember, T is years after 2000. And it's projected that in the year 2050, the population is now 10 million. That's what that is. And that means T equals 50. Now, we want to find A0 and K. Now, A0, is always the initial population. It's what we start with. So that one's a little bit of a gimme. We're starting with 6.04 million. That's our A0. So that means our f of t, which is A0, e to the kt. Well, we can now update it to be 6.04 e to the kt. Now we got to find k. Now it's projected that the population is going to be 10 million when we're 50 years away from 2000, or the year 2050, or t is 50. Now f of t represents the population. So that means 10 equals 6.04 e to the k times 50. And so now we got to use those skills from section 4.4 to solve for k. So we can divide both sides by 6.04. And let's see what kind of number we get. Is that going to be a manageable decimal? Ooh, it's kind of a hairy one. I'll just leave it as 10 over 6.04. And this is 50 times k. So now to get the k, I'm going to take the natural log of both sides. And so these will cancel out. And so we get the natural log 10, 6.04 equals 50 times k. So lastly, to solve for k, I'm going to divide by 50. So I'm going to get this. And there we go. That's k. So now I'm going to put this into my calculator. I want to try to not round anything until the very end if I can help it. So natural log of 10 divided by 6.04. I put that in my calculator. I get 0.504181081. Then I divide by 50. And I get this. Now, what they typically ask you to do is round this to maybe the second decimal place. I'll do that. But I recommend doing this at the very end, round at the very end. If you round along the way, you might alter the result enough to where you don't get the result that the text is looking for. Get round-off error is what it's called. You'll get the wrong answer because of rounding, even though you did all the calculations right. So that means k is 0.01. And so now our formula is this. Have something for this. And there we go. So now we have our formula. Oh, I'm sorry, not K. Ooh, we found K. It's T. There we go. So now we have our formula. Let's answer a question. And a question they might ask is this. Which year will Israel have a population of 9 million? When is this going to happen? Well, again, we're going to treat 9 million as 9. So there's some population, and it's going to happen at some t. Actually, you want to be careful drawing this arrow. We're going to put in a year t. We're going to get a 9 from our formula. Well, we don't know which t. We've got to solve for it. So we have our formula. We want to ask the question, for what value of t is the population 9 million? So again, we're going to solve this case very similarly like we did for k, but we're going to now solve for t. So divide both sides by 6.04. We get 9 over 6.04 equals e to the 0.01 t. Now take the natural log. We get log base e and an exponent base e. They'll cancel. But what we do to one side, we have to do to the other. And once again, these are going to cancel. So you get natural log 9 6.04 equals 0.01 t. Lastly, divide both sides by 0.01. And that's what we get for t. Now let's actually do that computation. And again, I'm saving all my computations for the end, so I don't lose anything due to the round-off error. But, I mean, what you could do is you could calculate this, write out all the numbers behind the decimal, take the natural log of that, write out all the numbers behind the decimal, divide that long number by 0.01, and then, well, you'll get your answer. But don't round. Try not to round until the very end. But I'll do natural log of 9 divided by 6.04. Get a number, 0.398820565. Divide that by 0.01, and then I get 39.88, and do the second decimal point is t. In this problem, let's see, in which year will Israel's population be 9 million? Well, if we take 2000, we add our 39.88, what we'll get is 2039.88. And they might want you to round it to the nearest year, because if you say, well, Israel will reach a population of 9 million by the year 2039, well, no. New Year's of 2039, that's not 2039.88. So Israel's population would be just under 9 million at this time. So what year, the safest one to say would be round up to 2040. Because when we talk about what year when something is going to happen, we usually sort of, well, by that year. So in 2039, I mean, you could say that, it sort of makes sense. But there's also periods in 2039 where Israel won't have a population of 9 million, specifically New Year's Day of 2039. So if you round the 2040, well, there you go. You're completely safe there. If you're going to hit 9 million here, you're definitely 9 million New Year's Day 2040. And assuming the population keeps growing, you'll be 9 million and above all the way through. So that could be one way of interpreting that. So anyway, so let's look at another one. So another one with decay. The half-life of krypton 91 is 10 seconds. So that's what they've told us. Now, let's see. If 16 grams is our initial amount, how much will remain after 10 seconds? So this kind of problem is an interesting one. There's some implied data here. So I'm going to show you how to set it up. Now, when we're talking about half-life, this means that the amount of the substance is going down, it's lessening. So this means in our formula, we're going to expect a K that's less than 0, negative K, or some K that has a negative value. And that'll tell us if we're on the right track. So it has a half-life of 10 seconds. Let's see here. We'll alter this one a little bit. Instead of asking how much will be there in 10 seconds, we'll try 10 and 20. We'll do both. So what it says is this. Because the half-life is 10 seconds, there might be an obvious answer here. I'm going to work through all the steps anyway and say it's not obvious. Well, that means after 10 seconds, whatever we started with, 10 seconds goes by, we're going to have half of it left. So when t is 10 seconds, whatever we start with, there's half of it left. So this means we can take our model and we'll get half of A0 when t is 10 seconds. In this case, we're going to use time is equal to 10 seconds. So we still want to solve for k. So we can divide both sides by A0. This is kind of a clever trick. And we end up with 1/2 equals e to the 10k. Take the natural log of both sides. Oh, that's 10k. And so we'll get cancellation. So we get ln 1/2 equals 10k. And then divide both sides by 10. Ln of 1/2 divided by 10 equals k. And again, we'll save the calculation towards the end. We don't want to lose anything to round off. And so sure enough, what we get, and I'm going to round this to, let's see, let me check what decimal place they want this at. Let's see, it doesn't say. Well, we'll go to the second decimal place here. So for me, that's going to come out to negative 0.07 is approximately k. So we got a negative k. That's a good sign. So now let's answer this question. And you might have figured this out. If the half-life is 10 seconds, how much is left after 10 seconds? Well, half is what is there. So let's try this out in our model. Let's see how well this works. So now our model, f of t, and they'll sometimes call this just capital A. Well, it's going to be our initial amount, 16, e to the minus 0.07 t. We found k. And our initial amount, we're going to start with 16. So what we can do is plug in 10 seconds. And we should get half of our initial amount, now close to half, because again, we rounded this off, so it's not going to be quite half, it'll be a little off. But we can do negative 0.07 times 10. Then we can do this calculation. And I'm just doing it stepwise, just so as not to make an error. And then times 16. And it comes out pretty close. And again, it's not going to be exactly 8 or half of 16 because again, we rounded this off. But it tells us that our formula is working. It's working well enough. So we get an A of 7.94536, which is about 8. It's pretty close to 8 grams. All right. So let's ask a little more technical question. How much of this will be there after 20 seconds? Well, again, f of t, we'll call it A. Use the same formula. Now we're multiplying K by 20 seconds. So we get 16 E, and it's going to be negative 1.4. Then we do this calculation. And so we get about 3.9456, which is kind of what we expect because the half-life is 10 seconds. So at 10 seconds, we have roughly 8. So 20 seconds, we go from 10 seconds to 20 seconds. Well, that's again that half-life, so we should have roughly 4. And sure enough, that's what we got. All right. Now, there's one more model to mention. And this is what's called the logistics formula. The logistic formula. And the idea is this. Growth in the real world. It's not indefinite. When you come up with models for population increase, things just don't keep growing. Populations just don't keep expanding. Eventually, they kind of level off. And so a formula we use for this that provides this leveling off behavior what is that? It's a logistic formula. Now, what it typically does is we have some initial amount. We could say right there. And what happens is, sure enough, things exponentially grow. But then they start to decrease the rate. They're still growing, but the rate of growth is decreasing, and then it levels off, kind of at a horizontal asymptote. And then you're heading towards a maximum population. So here your rate is increasing. So you're seeing exponential growth. And here you're still seeing growth, but the rate of growth is decreasing. It's not growing as much. Here, as you go day by day by day, you're growing maybe, say you're looking at, well, say rabbits. Rabbits are sort of known for this. Populations grow quite a bit. There's a famous relationship between rabbits and lynx. Lynx are sort of, like a bobcat. And their populations, how they grow. Lynx will grow population, and rabbits will shrink, and then the lynx population will shrink because there's no more rabbits to eat. So the lynx start to go away. And then when the lynx go away, the rabbit's population grows, And then with all these rabbits, the lynx start hunting more rabbits, and then the lynx population grows, rabbits population shrinks, and then the lynx population shrinks. It just goes on and on forever. And here you would say you have 2 rabbits a day, 4 rabbits a day, 8 rabbits a day, and then you get to like maybe 16 rabbits a day, and then it's 8 rabbits a day, and then there's maybe 4 new rabbits a day, and there's 2 new rabbits a day. And so the rate of growth, the addition of rabbits per day. So there's 2, now they're getting 4 a day, now you've got 8 a day, now it's back to 4 a day, now it's 2 a day. You still have growth, it's still increasing, but the rate of increasing is not as you have growth, but the rate of growth is decreasing. So let's take a look at this. Let's do something with one of these formulas. So let's say we have this. Let's say we have a flu epidemic, and we're going to model the population of people with this flu. So here we're just going to study the model. And so the model that we're given for this particular flu is this. And here they're going to tell us that let T be weeks. T is going to be weeks. So a question they might ask us, well, first off, let me talk about what this is trying to do. It's trying to model the number of people who have this flu, say in the flu season. And the idea is that the number of people who get the flu, it can start off really quick, and then it's going to level off. And then at some point it'll drop off. But it's going to start out quick, and then it's going to level off, and then people start to get over it, and then you'll see it decrease again. But to start, it's going to do this and then just level off. At least that's the assumption with the logistic model. So we're going to ask some questions. First off, someone's got to show up with this flu. Like so many people, maybe it's one person, maybe it's a handful of people, somebody has the flu at the very beginning. So how many people are we assuming is that? So how many people have the flu to start? How many have the flu to start? Well, that is T equals 0. So we want to look for f of 0. What is that? Well, f of 0 e to the minus 0. Now, e to the 0 is just 1. Anything that has a 0 exponent is going to be 1, except for 0. 0 to 0 is undefined. And minus times 0 is just 0. So we're going to get 5,000 times 1. It's a little clearer. So we got 100,000 over 1 plus 5,000, or 100,000 over 5,001. So divide that, and what you're going to get is about 19.996. And looking at the text here, and they're going to actually round that up. They're going to call it 20 people. Now, there could be arguments where you should round it always to 19 because you can't have 0.996 of a person. So some people might say, well, you might call that 19, but the text is going to say round up to 20. All right. So we might ask this question. See. So how many people have the flu at the end of the 4th week, or we've had 4 full weeks? How many people have the flu? Well, again, T was in weeks. So that means T equals 4. So we want F of 4. And minus T will now be minus 4. And again, this is one of those calculations where you don't want to round off until the very end. So let me be careful with this. I'm going to go E minus 4. I get a decimal number. Times that by 5,000. Get another decimal number. Add 1. And when I do that, I get 100,000. And I'm going to use as many decimal places as I can. And divide by that answer. And so I get 1,080 not 1.68. And here in the text, they want us to round down. Round to the nearest person is what it is. Not just round down, but round to the nearest person. And we've got that. So one of the things they're going to ask with this is the limit size. Now the limit size is what happens as t goes to infinity. So t just gets bigger and bigger and bigger. And so what happens, let's say let's just focus on e to the minus t. When t is 0, get e to the minus 0, and that was just 1. t to the 1. Well, that's e to the minus 1. I'll round this. Let's see what that is. It's about 0.37. Let's go t to the 10. Well, that means we have e to the minus 10. Remember, e was to the minus t. And so this is going to be or 5. It got small really fast. Whew. Let's go t to the 100. I don't think there's going to be much left. I get 3.7 about times 10 to the minus 44. To give an idea how small that is, zero point 1. I think that's 43 zeros and then that 37. That's a small number. This is just for 100 weeks. A year has 52 weeks, so this isn't even 2 years. So if we had t as 1,000, 1,000,000, I mean, this practically, e to the minus t practically goes to 0. So as t gets massively big, this e to the minus t will consider to be 0. It will go to 0. So to figure out our limit, we say the limit as t goes to infinity of 100,000 over 1 plus 5,000 e to the minus t. Well, as t is going to infinity, this is going to go to 0. So this will be 100,000, 1 plus 5,000 times, and for all practical purposes, we'll just call it 0. And so we get 100,000 over 1 plus 0, or 100,000 over 1, and then we get our limiting population. $100,000. So what this means is that we're going to start where 20 people have the flu. There's our population. This is in 2 weeks. So we start out at 20. I'll call this 100K for 100,000. And this is going to act as an upper limit. And so we're probably doing something like this, where we're going to try to level off at 100,000, starting at 20. All right. So the last sort of technical thing in this section, it's about rewriting exponential functions in a form that's base e. So the idea is this. We want to take y equals a to the bx, And we want to rewrite it something similar to the form of f of t equals a0 e to the kt. So how can we do that? And where do you come up with a model like that? Well, one model you could use could be bacteria growth. Let's say you have one bacteria. It splits into two. So now you have, we'll start it like this. It goes to the two bacteria. And then each of these split into two. And now you have four bacteria. And each of these they split into two, and we have 8. So we start out with 1, then there's 2, then there's 4, and then there's 8. So we could use a model like this. Y equals a to the bx. And we could call this time equals 0. That's where we started. Time equals, say, maybe it's an hour. 2 hours, 3 hours. So we could use a model like this. We know A is equal to 1. So that's our initial. So our formula is now 1 times B to the x. And we just need to find B. So we could use some data here. We could say, well, when t is 1, we had a population of 2. So let me replace this with a t. So if a population of 2 when t is 1. Well, b to the 1 is just b. So we get 2 equals 1 times b, and that just means 2 equals b. So now we know what b is. So now our formula is y equals 1 times 2 to the t. And we can try this out. Like when t is 0, we get 2 to the 0, which is 1. So we get 1 times 2 to the 0, which is 1 times 1, which is 1. And that's what we get at t is 0. That works. We could try t is 3. So we get 1 times 2 to the 3rd, or 1 times 8, or 8. And sure enough, when t is 3, we get 8. T is 3, we get 8. So that's how you could come up with those kinds of models. That's one way of coming up with it. So we had something 1 times 2 to the t. And that's our y equals a times b to the x. So what we might be interested in doing is expressing this, instead of using a base b, base e. How do we do that? Well, we can do this. There's a clever trick we could do, and it's this. Note, b to the x is going to be equal to e to the natural log of b to the x. And the reason that's true is that this is log base e, this is exponent expression base e. Technically, these will cancel and just leave you with b to the x. So we can replace b to the x with e ln b to the x, because these ultimately cancel, just leaving you that to begin with. So what we'll do is we'll now rewrite this as y equals a e to the natural log b to the x. And again, nothing's changed. Really, this will cancel, and that will give you a times b to the x. This will remain. But now what we're going to do is use our exponent rule. The log of something with an exponent makes the exponent hop down in front of the log. And now, since this is x times ln b, we can switch the order, because multiplication, the order doesn't matter. And so what we get is this. And so what we get, natural log of b is going to be our k. Now we could let x be t, and we get a e to the k t. So k becomes natural log of b. So let's take a look at that model we're using for bacteria. Y equals 1 times 2 to the t. We want to rewrite this as y equals, well, we're going to have a e to the natural log of b times t for us, because we're going to use t instead of x. Well, for us, a was just 1. And it's going to be e to the natural log of 2 t. So natural log of 2 it's about 0.69. So this will be approximately 1 times e to the 0.69 t. And then we'll just multiply by 1. So approximately we get 0.69 t. And then we did some rounding here. So there's going to be some issues with accuracy, but let's try it out. Let's see how well this works. Now, if you recall for our formula, at t is 3 hours, we had 8 bacteria. So if we let t equal 3, we get e to the 0.69 times 3. And this comes out to about 7.92. If we round to the nearest bacteria, that's going to be 8. So it seems to be working. So the basic formula, what we're going to be doing is this. If you have y equals ab to the x, we can rewrite this as y equals a e to the natural log of b times x. And that lets us restate this model as that model. So to do another example, let's say if y equals 100 times 4.6 to the x. Well, in this case, a is 100 and b is 4.6. So for our new formula, we want y equals AE, the natural log of B, x. And so we can say this will be y equals 100 e to the natural log of 4.6 times x. And they want us to compute this, and they want us to round it. It looks like to the second decimal place. So natural log of 4.6, it's about 1 to 1.5. Well, they want to go to the third decimal place. So 1.526. If we go to the third decimal place, we'll get this. And there is our transformed formula from this to that. All right. So the last thing to mention in this section, it is about modeling. And we have exponential functions, we have logarithmic functions. You saw the kind of curve that the logistic formula uses. When we talk about modeling, we're talking about fitting a model to data. And depending on how the model or how the data is shaped, it sort of gives us an idea what kind of model we want to use. So, for example, if we have data that's doing this, well, it's suddenly increasing. So this might want an exponential model. And a recommended model for this would be y equals ab to the x with a greater than 0, b greater than 1. And again, this is sort of what the exponential function looks like for b greater than 1. All right. But if you see something like this, well, here it's going to be another exponential model. It'll be y equals ab to the x. Again, a will be greater than 0, and b is going to be between 0 and 1. And this is like that exponential function we saw earlier with the base, say, like of 1/2. All right. One thing here, I see the difference between their, okay, I guess they're not, they're logarithmic functions. So that, these suggest an exponential function of some kind. Next, for logarithmic, say your data is like this. It might be recommended to use a logarithm to model this. Now, I'm going to go over what I mean by modeling. I guess I better get a little more detailed. When we talk about a model, we're going to try to come up with a curve that best fits this data, that best passes through like that. And so the kind of curve we're going to use to approximate these points on our graph would be, in this case, a logarithmic curve. For those other graphs, we would approximate with an exponential curve. Need a stronger red pen there. So this would be a b greater than 1. And then for the other exponential, we try to fit a curve like that. B between 0 and 1. So going back to this one, this logarithmic curve, what we would recommend, what the text recommends, is something like this. And for these parameters, a greater than 0, b greater than 0. Another use of the logarithmic, and again, now b here, note, it's not playing the role. This is a little different. With our exponential function, b was acting as a base. We had a times b to the x, where b was a base. Here, b's not a base. So in this next model, we're going to have b less than 0. Keep in mind, it's not a base, and it's also not inside a logarithmic function. So this b is just being multiplied, it's just any real number, really. So that could be confusing. In fact, I'll use a different b just so there isn't any mix-ups there. So you want to fit a curve like this through here. And the formula for this curve, and it's going to be some kind of logarithm. It's going to be y equals a plus, I'll say, capital B ln x. And so capital B in this case, this will be a greater than 0, which will lift this logarithm up. So when we did our logarithmic graphs, we had this one passing through the x-axis. If you add a, you could lift it up. And then capital B less than 0. All right. And finally, they have what are called linear distributions, or linear plots of data, rather. And you can see this. And you might fit a line here. The act of fitting a line is called linear regression, and you'll run into this in statistics. So this is linear. And we would use something like y equals ax plus b for a greater than 0. Another linear model that we might consider, well, if our data does this, the formula for a line that best passes through this data, best fits it. Again, we're going to be dealing with linear because it's a line. And then y equals ax plus b for a less than 0. So we could do this with different functions. You're not limited to exponential or logarithmic or lines, but these are actually pretty common ones. These are ones that people do use, especially if you're doing linear regression or any kind of regression or curve fitting. Well, I guess you could call it that. Not necessarily. No. It's some kind of regression. You're trying to come up with a line or a curve that best passes through these points. In other words, you place that curve or that line amongst these points, so it's as close to all of them as possible. And there's some formulas you can work with to do that. It involves some calculus. Well, that's it. That's 4.5. If you have any questions about that, let me know. Have a wonderful evening.